4.5 billion years ago, while Earth was still a molten hellscape, life somehow appeared in just 600 million years. Scientists call this impossibly fast. We believe life crawled from primordial soup, evolved slowly, and eventually created us. But what if we got it backwards? What if life rained down from space, carrying the genetic blueprints of civilizations that existed billions of years before Earth even formed? If you're ready to question everything you know about human origins, hit that like button and subscribe. We're about to uncover evidence that we might be the aliens. Prepare yourselves. We begin. Music. Picture trying to assemble a working smartphone by shaking a box of electronic parts for 600 million years. The math behind life's emergence on Earth breaks every rule of probability. When our planet finally cooled enough to support liquid water, something extraordinary happened within what scientists consider a cosmic blink. Complex molecules started organizing themselves into self-replicating systems. These weren't just simple chains of carbon and hydrogen. We're talking about intricate biological machines capable of copying themselves with stunning precision. Think about this timeline. Earth formed 4.5 billion years ago. For the first 800 million years, our world was basically a giant lava lamp, constantly bombarded by asteroids and comets. The surface temperature reached 2,000 degrees F. Nothing could survive. But somehow, by 3.8 billion years ago, we find evidence of complex microbial life already thriving in the fossil record. That gives evolution just 600 million years to go from sterile rock to living organisms. Charles Darwin himself called this rapid appearance the warm little pond problem. He knew that natural selection needed time, vast amounts of time to create even the simplest life forms. Yet, here on Earth, life appeared almost immediately after conditions became suitable. Consider the complexity we're dealing with. Even the most basic bacteria contains roughly 4 million individual parts working in perfect harmony. DNA, RNA, proteins, cell membranes, energy production systems. It's like finding a fully assembled Boeing 747 in a junkyard where only raw materials existed the day before. Modern scientists have tried recreating these conditions in laboratories. They've mixed all the right chemicals, applied electrical charges to simulate lightning, and waited. The result: a few simple amino acids, the building blocks of proteins. Nothing even close to a living cell. The gap between chemistry and biology remains as mysterious today as it was in Darwin's time. But there's another explanation that makes the timeline make sense. What if life didn't start from scratch on Earth? What if it arrived here already assembled, already tested, already proven to work? Imagine life as a cosmic inheritance passed down from civilizations that figured out the biological puzzle billions of years before our solar system even existed. This isn't science fiction anymore. NASA has found organic compounds throughout the galaxy. The European Space Agency has detected complex molecules in interstellar clouds. The building blocks of life aren't rare cosmic accidents. They're everywhere we look. The Panspermia hypothesis suggests that life spreads throughout the universe like seeds on the wind. Some seeds land on suitable planets and take root. Others drift through space for millions of years waiting for the right conditions. From this perspective, Earth wasn't the birthplace of life. It was just another garden where cosmic seeds finally found fertile ground. If this theory holds true, then every living thing on our planet, including us, carries the genetic memory of civilizations that existed long before Earth was even a glimmer in a stellar nursery. But the evidence goes far deeper than just mathematical probability. Hidden inside the rocks that constantly rain down on our planet, scientists have found something that challenges everything we thought we knew about life's origins. Every single day, Earth gets hit by 100 tons of space debris. Most of these cosmic visitors burn up in our atmosphere, creating the shooting stars we wish upon. But some survive the journey, crashing into our planet as meteorites. For over a century, scientists have been cracking these space rocks open, expecting to find minerals and metals. Instead, they've discovered something far more extraordinary. The Murchison meteorite changed everything. When this 4.5 billion-year-old rock slammed into Australia in 1969, researchers found something impossible inside. Amino acids. Not just any amino acids, but 74 different types, including many that don't exist naturally on Earth. These weren't contamination from our planet. The chemical signatures proved they formed in deep space. Think of amino acids as biological Lego blocks. Every protein in your body, from the hemoglobin carrying oxygen in your blood to the enzymes digesting your food, is built from these essential components. Finding them in a meteorite was like discovering a construction kit for life floating through the cosmos. But the Murchison meteorite wasn't alone. The Allende meteorite, which fell in Mexico, contained even more complex organic compounds. Scientists found nucleotide bases, the letters that spell out genetic codes in DNA and RNA. The Murray meteorite revealed sugar compounds that form the backbone of genetic material. The Carbon Hill meteorite contained lipids, the building blocks of cell membranes. Here's where things get really mind-bending. Some of these meteorites are older than our solar system. They formed in stellar nurseries billions of years before Earth existed, carrying their biological cargo across unimaginable distances and time spans. It's like receiving a message in a bottle from civilizations that lived and died before our sun was even born. Recent analysis has revealed something even more shocking. Some meteorites contain microscopic structures that look exactly like fossilized bacteria. These aren't random mineral formations. They have the distinct shapes, sizes, and internal organizations of living cells. The ALH's 84,001 meteorite, originally from Mars, sparked intense debate when NASA scientists claimed to have found evidence of ancient Martian life preserved in its rocky matrix. The implications are staggering. If meteorites regularly carried organic compounds throughout the early solar system, then the building blocks of life were being delivered to planets like a cosmic Amazon service. Earth, Mars, Venus, and the moons of Jupiter and Saturn were all receiving the same biological packages from deep space. This delivery system is still active today. Every time you see a meteor shower, you're watching potential life seeds rain down on our planet. The Perseid meteors, the Geminids, the Leonids. Each streak of light represents organic compounds being deposited in our atmosphere. Some scientists now believe that Earth's early bombardment period, when asteroids and comets constantly pelted our planet, wasn't just a destructive force. It was the universe's way of planting a garden. Each impact delivered new genetic material, new biological possibilities, new evolutionary pathways. But if meteorites can carry life's building blocks across space, the next question becomes even more extraordinary. Can actual living organisms survive the journey? The answer lies in the most extreme creatures on our planet. Organisms so tough, they seem designed for interstellar travel. Earth sits in the most perfect spot imaginable, 93 million miles from a perfectly sized star. We call this the Goldilocks zone. Not too hot, not too cold, but just right for liquid water to exist. Move us 5% closer to the sun, and we become Venus with surface temperatures hot enough to melt lead shift us 10% farther away, and we turn into Mars, a frozen desert where water exists only as ice and vapor. The mathematical precision is breathtaking. Our planet's orbit varies by less than 2% throughout the year. Our moon is exactly the right size to stabilize our axial tilt, preventing wild climate swings that would make complex life impossible. Our atmosphere is 78% nitrogen and 21% oxygen, a combination so chemically reactive, it should have burned away billions of years ago. Yet somehow this delicate balance has remained stable for billions of years. The odds of this happening by chance are so small that scientists struggle to express them mathematically. It's like flipping a coin and getting heads 10,000 times in a row. But here's what makes the Goldilocks problem even stranger. Earth wasn't always this perfect. 4 billion years ago, our sun was 25% dimmer than it is today. By all calculations, our planet should have been a frozen snowball, completely inhospitable to life. Scientists call this the faint young sun paradox. Yet somehow, during this supposedly impossible period, life not only existed, but thrived. The geological record shows clear evidence of liquid oceans and complex microbial ecosystems. Something was keeping Earth warm when it should have been cold, maintaining conditions that allowed life to establish itself and spread. Traditional theories struggle to explain this. Some scientists suggest massive volcanic activity created a greenhouse effect. Others propose that early Earth had a much thicker atmosphere. But these explanations require a series of coincidences so improbable that they strain credibility. The Panspermia hypothesis offers a different perspective. What if Earth's perfect conditions aren't accidents, but engineering? What if advanced civilizations, facing the death of their own worlds, didn't just send out genetic material randomly? What if they deliberately chose target planets and modified them to be suitable for life? Consider the precision required. You'd need to adjust atmospheric composition, orbital mechanics, magnetic field strength, and planetary rotation. You'd need to account for stellar evolution, ensuring your chosen world remained habitable as its star aged and brightened. This level of terraforming would require knowledge and technology far beyond our current capabilities. Evidence for this kind of deliberate modification might be hidden in plain sight. Earth's unusually large moon, for instance, could be the result of an intentional collision designed to create tidal forces and stabilize our planet's rotation. Our magnetic field, generated by a liquid iron core, protects us from deadly solar radiation in a way that seems almost too convenient. Even our position in the galaxy appears optimized for life. We orbit in what astronomers call the galactic habitable zone, far enough from the galactic center to avoid destructive radiation, but close enough to benefit from the heavy elements created by dying stars. If Earth was deliberately prepared as a biological laboratory, then the next question becomes crucial. What kinds of organisms could actually survive the journey from their dying worlds to our carefully prepared one? Deep in the Atacama Desert, where it hasn't rained for over 400 years, scientists have found bacteria thriving inside rocks. These organisms, called endoliths, live in conditions that would kill almost any other life form on Earth. No water, no oxygen, no organic nutrients, and radiation levels that would be lethal to humans. Yet, they not only survive, but reproduce, creating entire ecosystems in what appears to be solid stone. This discovery led researchers to a startling question. If life can exist in Earth's most extreme environments, what about the ultimate extreme environment, outer space itself? The answer came from experiments aboard the International Space Station. Scientists exposed bacteria samples to the vacuum of space, where temperatures swing from 250 degrees below zero to 250 degrees above. No air pressure, no protection from cosmic radiation, no nutrients, no water. These conditions would kill a human being in seconds. The bacteria not only survived, but continued to reproduce. Dinococcus radiurans, nicknamed Conan, the bacterium, can withstand radiation doses 3,000 times higher than what would kill a human. It can survive in a complete vacuum for years. When its DNA gets shredded by cosmic rays, it simply rebuilds itself using internal repair mechanisms that scientists are still trying to understand. Tardigrades, microscopic animals that look like eight-legged bears, are even more impressive. They can shut down their metabolism completely, entering a state called cryptobiosis, where they're neither alive nor dead. In this state, they can survive temperatures of minus 458 degrees F, just a few degrees above absolute zero. They can handle pressure 6 times greater than the deepest ocean trenches. They can go without food or water for over 30 years. But here's the truly mind-bending part. When researchers exposed tardigrades to the vacuum of space for 10 days, 70% of them came back to life once they returned to normal conditions. They resumed eating, reproducing, and behaving as if nothing had happened. These aren't isolated examples. Scientists have found bacteria living in nuclear reactors, in pools of concentrated acid, in boiling hot springs, and in Antarctic ice that's been frozen for millions of years. Each discovery expands our understanding of life's incredible resilience and adaptability. If organisms this tough exist naturally on Earth, imagine what kinds of life forms might exist on planets with even harsher conditions. Worlds orbiting dying stars, planets with thick, toxic atmospheres, moons covered in radiation, bombarded ice. Life might not just survive in these environments. It might thrive. This changes everything about interstellar travel for living organisms. We used to think that life was fragile, requiring perfect conditions to survive even short journeys through space. Now, we know that some Earth organisms could potentially survive trips lasting thousands or even millions of years. The implications are staggering. If bacteria and tardigrades can survive in space, they could be hitchhiking on asteroids and comets right now, traveling between star systems like biological stowaways. Every meteorite impact could be delivering not just organic compounds, but actual living passengers from distant worlds. But survival is only half the equation. For Panspermia to work, these cosmic travelers would need to find suitable conditions for growth once they arrive. The question is whether Earth's fossil record shows any evidence of sudden biological arrivals that can't be explained by gradual evolution. Charles Darwin called it the most serious objection to his theory of evolution. The fossil record, which should show gradual transitions between species, instead reveals something far more puzzling. Complex life forms appear suddenly, fully formed, with no clear ancestral lineages.